Okay. Uh, so, uh, did either of you do the homework? Which is to just derive this from this. It's not very hard.
I forgot to take it.
The idea is you just replace.
I think it's even
You
in
just
Landau.
Of course it is. It's in
Yeah, it's
Zeldovich and
there.
Razier.
Because I think I saw that.
I mean, that's where I got it. Uh, but the point is that you can replace pressure dP with d rho c squared, where c squared is dP d rho. And we're going to be doing a lot of that. So now we come to de Laval nozzles.
Can you also write c square as p over rho rather than differentials?
Then it would mean something else. Unless dP d rho equals p over rho,
Yeah, in general it shouldn't be.
sometimes it equals 1/3.
It's also
Well, it's on the order of p over rho, but there's generally a numerical coefficient. Alright, let's say you have flow through a nozzle that's very thin. So to good approximation, we can say the flow is in the x direction. And at each point, the radius of the nozzle is a fixed quantity. And we can say that the velocity is approximately the same at each point. Strictly speaking, if the walls are viscous, it would be the cosine of the width of x times the width, but the walls don't have to be sticky, and the walls don't have to be sticky, and the point is that we're assuming the velocity varies along x, but not terribly much perpendicular to x. And then the equation of conservation of mass is just rho VA equals a constant. Okay?
Yeah.
Now that can be rewritten as follows. Namely, just if this is a constant, then the log is a constant, which means d log of the left-hand side equals 0. And that's this. And that means we can eliminate d rho over rho if and when we need to. Okay, now let's consider the second law, which is just the x component of the gradient equation. And in steady state, this is the equation of motion. Notice that I'm going to multiply by dx. I'm going to get dp, and I'm going to divide by rho. And then I get this. Now I'm going to substitute dp for dp d rho times d rho. I thought, as promised, I'm going to call this c squared. In this case, the sound velocity squared. Now this is not the adiabatic derivative. It's not.
It's full derivative, right?
It's the full derivative, and if the flow has heat conduction, then it's not exactly adiabatic. But you pretend that you know dp d rho along the flow. And
Is it still the sound the velocity?
no, not necessarily. But it's generally going to be of that order. And the point is, if you have an equation of state that p is rho to the 5/3, or rho to the 4/3, or rho, so the variation in the sound speed is 20-30%. Okay, anyway, substituting for this in here, we just write v squared. And now this d rho over d rho is just these two terms here. So we substitute for d rho over rho in here. And we have a 1/2 dv squared. So then look what we get. We get the dA over A is equal to dv squared over v squared times this quantity. Now what does that show, if nothing else? It shows that v equals vs where A is a minimum. Because where A is a minimum, it means dA is 0. dA dx, if you will. And this is dv squared dx. So that's exactly v squared equals vs squared. Now, that's very strange, because suppose you have a hot gas and it expands. You figure eventually, if it expands enough, it's going to
Slow down.
no, it's going to
Or it sounds good.
achieve its sound speed, because it'll cool off. It's going to cool adiabatically, and but if it's just expanding, it never becomes supersonic, unless it always was supersonic. Because dA over A is positive, and Vs squared over V squared was, let's say V squared was less than Vs squared. Yeah, what does happen? That's a good question. Suppose V squared, it's subsonic flow, so this is greater than 1, and therefore this is negative, and dA is positive. It just can't be. It means you don't have a steady state. Now, I don't know what you do have. I think that you have some kind of similarity flow where, a ball of gas, and you suddenly let it expand. It gets, I have to admit, I don't know what the solution is. But I know that you can't just have a steady state solution where you're feeding in more gas and it's flowing out and becoming supersonic. It seems that if dA over A is positive, the point is, I think that what you don't, since it's not just that I don't know the solution of the equation. It's that the equation doesn't have a solution because dA over A is positive, and this.
Sorry to ask you, what is it?
Oh, A is the area.
It doesn't mean that
Of the
it just
pipe.
gets small?
No, DA
Wait a
over is
minute.
negative.
Wait. Okay. Let's think about this. It means that as A gets larger,
It's negative, right?
V squared.
Is it an also?
This is a negative quantity, and in order for the left-hand side to be positive, this must be negative. So it has to, so dV squared has to be negative also. In other words, the flow has to slow down, even though the area is getting bigger. And it's very counterintuitive. I've never really felt comfortable with that. I don't understand.
It's not supposed to be slowing down?
What?
It's not supposed to be
Yeah,
slowing
I
down?
thought it should be slowed down
Okay, explain to me why.
because of
Conservation.
conservation. Yes. Because if you have rho v a should be constant, as you said. So if rho is constant and
Well, rho isn't constant, but I guess the point is
if
that it's.
a is getting bigger, so v
It
should
could be.
decrease.
Let's suppose it was constant. Let's suppose you had an incompressible fluid like water,
Okay.
expanding, even if it's under high pressure. Now I know that when I want to shoot water fast,
You have to contract
I
it.
have to stick my
Right.
thumb over it so that the pressure builds up and shoots it. That I can intuit it, but
That's exactly it.
I know. If you want to have a pressure gradient push, the point is if the area goes up, either the velocity goes down or the density has to go up. But if the density goes up, it means the pressure goes up because we're assuming the sound speed is positive, which means the PD rho is positive. So if the density has to go up, then the pressure has to go up, and that slows the fluid down. And if the pressure goes down, conceivably if the pressure goes down,
Density goes
sorry. Let's say I had the pressure and density going down, but the velocity went down even faster. That's no good because the pressure is positive. It has to be accelerated. It's pressure gradient. The pressure is going down. It has to accelerate the flow. So let's see. If the pressure goes down, I can push the flow outward. Velocity goes up, but then I don't get conservation of mass.
You must have conservation of mass. What enters
I know.
comes out.
So, no, in steady state. So maybe I'm saying what you probably just get is not a steady state. You probably get a rarefaction wave that propagates inward, and it disappears, but not in a steady way. In other words, if you're not constraining it, it just well, let's see. If it were water, and the width of the hose expanded, but it's incompressible, what would happen? It would let's say there's no gravity, So it can just stay. So it's just floating. Um, if you feed water in, I just don't know what would happen. If I feed water into a hose and the hose is getting fatter as the water goes along it, what
I think
happens?
it has to slow down. It has to slow down.
It has to slow down.
It's just like in.
In other words, it has to wait till it gets more stuff to fill up the hose.
You can look at.
But you see, if it slows down, then there's an edge, and at the edge there has to be a pressure gradient going out because in a vacuum the pressure has to be zero.
Maybe there's some temperature change also.
Forget the temperature change. We're talking about a vacuum. There's no water there. It doesn't matter what the temperature is. It's zero pressure because there's zero density.
Okay.
So I think what happens depends on the details. On the compressibility. Um, but if it's very soft, um, the pressure probably goes down. We'll, anyway, we'll see in a little while.
How does the profile of speed of sound look like in this nozzle?
We'll see that too. I'm just trying to figure out what would happen if you did this. And if you assume steady state, I think you can always assume steady state. The speed has to go down. And the pressure, I guess, at some point builds up. If it hits, uh, no, but then it has to hit something. It keeps the pressure, allows the pressure to expand out. I mean, it's easy to say it has to slow down, but in order for the fluid to know it has to slow down, it has to know that the pressure is increasing. And if you're expanding into a vacuum, the pressure wouldn't increase. So that just doesn't happen. I guess you just never get a steady state solution. It's probably a similarity solution. It just keeps expanding slowly.
But if that's the case, why questions don't show that? Mathematically, you can't solve this, right? There's no.
You can solve a time dependent.
No, the steady state question. You can solve it, right?
Under the assumption that you have steady state. But if that assumption is wrong, then you haven't solved it.
Okay, so if I suppose I have steady state.
But it may be that you don't.
Maybe I don't. So I suppose that I have steady state. I solve the equations.
Yeah.
And I look at the equations. If I see something is wrong there, then my assumption is wrong. That's what I'm saying.
Yes.
So.
And by the way, this is not an easy matter because there was great controversy in the 50s, which we'll also discuss soon. Anyway, the point is that in order to have a transonic flow, in other words, a flow with a sonic transition where it goes through the sonic point, you need for the area to decrease while the flow is subsonic but accelerating, and you need it for the area to increase when the flow is supersonic and still accelerating. So when this side is zero, it's called the sonic point. It's when the term in the brackets vanishes. And that's the neck of the nozzle. Okay. Now, this is a diversion in uniform fluid, one-dimensional isentropic. Okay, by the way, these are the missing equations, I think, from last time. I think what happened is she just typed things in the wrong order. But this is actually the homework.
But I think it's
Who was
misleading.
mentioned her? Who was?
Who is her?
She was a undergraduate senior who majored in chemistry, and she typed these notes from my handwritten notes. This, I mean, these are the notes, handwritten, which I can refer to. But apparently, part on uniform fluid 1D isentropic flow. This was the part that was missing yesterday, and there's the Lagrangian derivatives and D and so forth. Anyway, somebody like Arca has to put those two together.
Some mistake in copying, I guess.
What?
I think he copied in the reverse order. When it was copying.
When it was copying and pasting.
Yeah.
Maybe. Okay. Anyway, let's go back to nozzles. Same as before, but now I put in gravitation. So G is the gravitation, rho G is the gravitational force. I do the same thing as before. I'm going to have one extra term, d phi. And now instead of dA over A equaling this term, which I had before on the right hand side, there's this extra term d phi over B squared. So now if d phi is increasing, dA can increase at the sonic point. This doesn't have to be zero. Doesn't have to be the neck of the bottle, because if going outward you're going to a higher gravitational potential, then as long as the second term balances the first term, the left-hand side will be zero, and you can have a sonic point there. So for spherical outflow, dA over A is dr squared over r squared, and d phi is equal to this. So substituting for these terms, the left-hand side of the equation now becomes this, and it's clear I have a sonic point when the left-hand side equals 0, which is r is 2 gm over 2 times the sound speed squared. And this is kind of like an event horizon. I don't want to push it too far, but gm over c squared is a Schwarzschild radius, and I think there may even be a 2 in there too, but I'm not sure. Is it gm over 2c squared, Schwarzschild radius? So there you go. You have, and people use this to try to get acoustic Hawking radiation. This is the way modern physicists they look for thermal fluctuations which come out of a sound event horizon or something. But here the event horizon is in the supersonic part. In other words, the sound wave generated outside the horizon cannot get back, whereas the sound wave generated inside the horizon can get out. So actually, it's inside out event horizon, and uh, yeah. So if it was, even if you had a temperature of 0, you would have quantum fluctuations in the acoustic modes that would be radiated at the event horizon. Um, People actually try to look for that so that they can verify Hawking radiation. It seems to me if you make a flow, though, you have all sorts of things besides quantum noise generating fluctuations. But anyway, now here's the point. The solar wind. I tell the story to most of my classes, so I'm sure some of you heard it before, that people knew that there was something coming from the sun for hundreds of years because they saw comets, comet tails being blown back. And sunlight accounts for some of it, but it doesn't account for all of it. I mean, there are different, comets have different tails. The dust is blown by sunlight, but the gas is blown by the solar wind. So they knew there was something coming from the sun, and I guess most people just assumed it would pass through the corona. But Parker realized that you can't have plasma passing through other plasma. It's unstable. And that was what we just discussed. If you have plasma passing through other plasma, then the distribution function looks like this. This is the beam of particles passing through the thermal plasma. And in this region of the curve, you're going to have a positive derivative, and it'll be unstable to make plasma waves. And if he would have thought about it, I guess, enough, he would have realized that you can get, you can just fill in this part. You get quasi-linear evolution until it's flat, and then you would still have a beam. It turns out this is unstable for other reasons, but anyway, rightly or wrongly, Parker just didn't believe it could get through the corona. And the only solution he saw was that the solar wind is the corona. And that was a new concept that, people hadn't thought about. But the corona is hot. If part of it, if you extend the solutions of hydrostatic equilibrium, you can get a hydrostatic solution that goes indefinitely. But you would find that the corona would taper off very slowly. I mean, it would reach the Earth. That's the way he used to put it. And we're at the Earth. We don't see any signs of a solar corona extending out to the Earth, but we do see a wind. So he just figured that, okay, I'll solve the dynamical equations. And if he would have solved the dynamical equations, he could have gotten I'm missing some figures here. I just have to draw it in my hand. So let's make this R. And let's make this v squared, and this will be vs squared. And this will be, let's call this r sub s. So this is the critical point where both sides of the differential equation equal 0. Now, you can just do the signs of how the solutions look, because you can write first of all, this doesn't look right. This here, it's both terms are proportional to dr, and here both terms are proportional to dv squared. So you can just write dr I think we just need it. No. My goodness, what did she do? Alright, we're just going to have to work this out. Let's do it over here. dr times vs squared over v squared times 2r over r minus gm over v squared r squared is equal to 1/2 v squared over v squared. Now, seem to have a v squared in every term here, don't I? So I can just get rid of this. And anyway, this tells me, depending on the sign of these coefficients and this coefficient, and this coefficient, I know the sign of dr over v squared. Now, when I'm subsonic, this term is positive, and when let's just rewrite this as 1/2. No. Let's write this as dr times vs squared times 1 minus there was a square here, wasn't there? Okay. Is that right? Yeah, I think so. If I just take out the vs squared, I have a gm over here. I guess I just want a 2 over r here, and then I'm all set. Anyway, when rs is less than r, when r is less than rs, this is negative. And when v is less than vs, then this coefficient's negative, so both coefficients are negative, and that means that dr dv squared is positive. You got it, because these have the same sign, therefore these have the same sign. Or they could both be negative. So the point is, I have all these curves. Now, the slope has to go to 0 if the left-hand side goes to 0 and the right-hand side doesn't, which means I'm crossing this line here. Then these all have to have 0 slope when they cross it. And then on the other side, they have to go down. And that was what we were saying before, that the area increases, velocity has to decrease. Now, you can also have a case where the right-hand side goes to 0 and the left-hand side, the coefficient on the left-hand side didn't. And that means that dv squared has to be infinite. dv squared dr has to be infinite. So all the curves that cross this line to the left of the critical point have to do it with infinite slope, right? And then they have to reverse sign. So all these solutions are totally unphysical because you end up having the fluid at two different times is in the same place. It really corresponds to, the only thing I could think of is that you're throwing things up and they fall back down because you threw them.
But with two different velocities. It's not symmetry at the same point.
Just a second. Yeah, you're right. You're right.
Good point.
In one case, it's yeah, and the acceleration is infinite, so that doesn't look very promising. Yeah, so these solutions are just totally non-physical. Like we said, you get a solution and it's non-physical, you just have to say your assumptions were wrong. Okay, and similarly, you can have solutions that do this. Let me erase this, it's annoying now. You can have solutions that do this. Now these are actually, they are physical, but it's just that they start off supersonic, decelerate, and then they stay supersonic. Now, when there's no gravitation, you can also have those solutions. In fact, you can have them through a nozzle, because as the flow is supersonic, it slows down as the area constricts, and then it speeds back up again And I think that's what's called a ramjet. I think their jet engines actually designed under the principle. You get it going supersonically, and then you can burn fuel and get supersonic outflow at the back end. But
What's it called? Ramjet. With the S?
ramjet, R-A-M-J-E-T. It's one word, and it's where you just it's flying supersonically at all times. So the air is intaken at supersonic velocities. And then, of course, you have these solutions, which are also unstable. And then you have one more solution, which is called the critical solution, and it passes through the critical point. And you can also have this solution you can also have this solution where it accretes subsonically and passes through the critical point. And since this is v squared, the sign could be either way.
Yeah.
But then when it accelerates as it gets closer and closer to the object, and hits the object supersonically, and that's actually pretty reasonable. If you drop something from a large distance, it would fall and at some point become supersonic. And this was used as an accretion solution by Bondi. He solved the equations for accreting gas onto an object. But this critical solution was Parker's idea for the solar wind. And this was 1957. I think this was 1951. I'm not sure. 50 or 51.
But he said that this is exactly the path it takes. It's really.
Yeah, he said through the critical.
From all the passes there is the
That's right. That's right, and that's why nobody believed him, because they said it has measure zero. It's pathological solution. It wouldn't occur in nature because it has measure zero. It's one out of an infinite number. And actually, Chamberlain argued that you would have these solutions, and this is called the solar breeze solution, because it never goes supersonic. It never goes supersonic, and eventually it slows down. And in order for it to slow down, the pressure has to increase. So the idea is that it's subsonic, but very dilute. But as it passes the critical point, it starts to feel the interstellar pressure. And it's true, if the interstellar pressure were as large as the pressure on the sun, or comparable to it, it would accelerate and then gradually decelerate as it. And by the way, this solution is valid after a supersonic flow passes through a shock. Like we heard the lecture on the Crab Nebula yesterday. So it's highly supersonic, but then when it passes through the shock, it's subsonic. And all these people like Reese and Gunn and Kendall and Carnegie, who we were laughing about yesterday, they actually used the fact that after the shock, the fluid slows down because uh, it will expand as much as it has to until it's balanced, until the ram pressure, rho v squared, is balanced by the um, interstellar pressure, pressure of the interstellar gas. At that point, the pressure behind the shock, when when the ram pressure is converted into heat, so the pressure behind the shock is about equal to rho v squared ahead of the shock. It's the momentum flux. We'll get to that in a minute, next week. But then it can't keep flowing. I mean, at some point the interstellar gas has to stop it, and at least divert it. So if you have a spherically symmetric solution, it would have to slow down until the velocity was zero, and then it would have to be in pressure equilibrium with the interstellar gas, which means that slightly before, the shock had to form itself where the pressure was slightly below the interstellar pressure, and then it gradually gets and slows down. It's like something landing on the ground. There's a shock wave, and then it settles, and by the time it hits the ground, it better not be moving. So these breed solutions are valid post-shock, but the numbers in the solar wind just don't work out. I mean, the pressure in the corona is much higher than in the interstellar medium by so many orders of magnitude that when you think about it, this really is the only reasonable physical solution. And
That seems very, very strange.
and there was this other guy named Chamberlain, oddly. I think in the 20th century, if you were named Chamberlain, you were you, you were destined to play the role of a historical turkey. But I mean, I think this guy Chamberlain in astrophysics, met up with the same ignominy as Chamberlain and as Neville Chamberlain, who made the peace treaty with Hitler. He insisted that Parker was wrong. I think he was older than Parker and more established. But they sent up. This was the late 50s, so the U.S. was just getting its space program going, and by 1961, I mean within 3 or 4 years after Parker wrote the paper, instruments on one of the early U.S. satellites to escape the Earth successfully. They measured the solar wind. I mean, they had particle detectors that measured their velocity, the velocity of the particles, and the velocity of the particles as measured by the instruments were, it had a slight spread, but the spread was much less than the velocity themselves, which means the thermal delta V was much smaller than V, which means the flow was supersonic. And Parker actually told me that even then Chamberlain wrote a paper, explaining the data using the solar breeze solution, and the editor of APJ at the time was Chandrasekhar, and they were all in the same building at the University of Chicago. So Chandrasekhar got the paper, and he walked over to Parker's office and said, "What do you think? Should I publish this?" And Parker looked at it and he said, "Well, if you do, I'll be happy to write a one-page paper explaining why it's wrong." And Chandrasekhar then took the paper and went over to Chamberlain's office and convinced him not to publish it or something. And I don't think Chamberlain was ever heard from again. I mean, the only thing I ever heard about him was that he threw this home run pitch to, uh, and was just he, he he put all he put all his marbles on one horse, and he was just totally wrong. Um, so what time is it? It's after 3.
These different lines are basically different initial conditions then for the source. Since you have thermal distribution, you always
It's
have
different initial conditions, but in the case where it's subsonic, you have to make sure that the outer conditions also match.
Yeah, but since you always have thermal distribution, you have large distribution in velocity space, you always have some particles following this trajectory, and then you have some other particles filling in those with locations in velocity space.
If it's collisionless, maybe.
Yeah. So you always have some particles going like that.
If there's no magnetic field, then it's totally collisionless. Yeah, I mean, some particles escape the Earth's atmosphere too. Um, and I don't know. I've never thought through all the treatments and all the approaches in great detail. Um,
What is this characteristic weights here?
oh, this is RG is basically it's the point at which an object going at the sound speed would be the escape velocity from the sun. So in the case of the solar wind, it's like 2 solar radii. It's fairly close to the sun, and that's the scale. That's the scale here. Everything has to be decided within about 10 to the 11th centimeters of the
So
sun.
if we look on at large distances, what we see is only this. This will fall down.
That's right.
Only
That's
this
right.
will
We live way out here.
So it's not as no, it's very understandable why we see only this.
Yes, exactly.
There are
That's
all
the
of
point.
them, and they decrease, and that's that's what remains.
It's not that these decrease because these might have a much higher density.
Okay, but their
Than this.
velocity.
It's just that they. It's just
Their
that they.
velocity.
It's just that they're not solutions.
Those.
No, they're solutions, but they're not the solutions that nature picked. Because if nature would have picked them, the pressure at this point would have had to increase with radius from there on, and that does not correspond to. Anytime you have subsonic flow everywhere, it means that every part of the flow can communicate with every other part, because the communication takes place at the sound velocity. And in that case, it's not enough to feel the initial boundaries. You also have to make sure you respect the final boundaries. So if it's not a solution because of the boundary conditions, then tough. And the thing is, here you still have the ram pressure, but then the correct thing is to connect it to a shock wave, which then drops it down. To one of these solutions, but that's already at a much bigger scale. I mean, I'm not drawing it to scale, but I should be way off screen when that shock happens, and it should just pick one of these solutions that corresponds to interstellar pressure, but none of those solutions are going to necessarily be the ones on this graph, because the ones on this graph um, were particular to the sun. I mean, this RS and VS has to do with the conditions in the solar corona and the sun's gravitational field. And what happens at the solar wind termination shock, which is like 50 AU, it's actually like 100 AU. And by the way, the termination shock has been crossed, and the outer sheath has also been crossed. So I think Voyager is now actually in interstellar space. It's very exciting. Um, but the termination shock was only passed 6 or 7 years ago.
I think that Darwin
Da-
used this data
yeah,
in
yeah, 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 yeah. Ariane.
yeah, with the new.
Um, but and there, well, you have neutral particles. It's actually pretty complicated there. Anyway, that's the solar wind story. And, next time I guess we go back to shockwaves. Right. Did we stop this? No, we didn't.